Hi class, it's Bill Berry back with another video regarding trees. Binary search trees specifically is a big focus for us this week in our Java 2 class. We have had a couple of videos setting things up, giving you basic terms, talking about the x equals change x, importance of that little algorithmic pattern. We also introduced the add method and how to set up trees, create the nodes. So we're zooming along here pretty well. We have a couple other ones that we want to hit on here, a couple other methods. So let's jump into that. And we are in our tree creation. Notice last video we talked about nodes, creating the trees, we talked about the add algorithm, we talked about the pseudocode, we walked through that, we looked at the code, so hopefully all of that makes good sense to you. We're going to look at one more algorithm here and then we'll look at the code for that. Contains is another one that is common, right? You need to be able to ask, hey, is this particular number in the binary search tree in question? Now, if you have numbers like these, 3 or 2 or whatever, you need to be able to walk through the tree and figure it out. Now, one of the things that's great about a tree is the speed at which this can happen. If we have a height balanced tree, we can do this at an amazing speed, and if you think about the complexity here, every time you make a decision based on the tree data, you've cut the problem in roughly half. Every time you've decided whether to turn left or turn right, you've cut the problem in half. So that means that you are looking at a big O, a complexity of something like log n, right? Log base 2 of n. That means that your tree can get really big, but your speed doesn't get big nearly as fast. So these are very fast algorithms, right? A log n algorithm is pretty darn good. So how does this particular one work, and then how do we implement it recursively? Again, makes sense. Once you've seen add and you've seen this, you kind of should have pretty much of a good idea of how to use recursion to your advantage here. So let's say that we wanted to find out, do we have a 3 in the tree? Remember, of course, we've got our root pointer up here, and the root pointer points to the first node in the tree. So if we want to find out whether there's a 3, the first thing we're going to have to do is follow the root pointer. Got to start there. But if you have looked at it, if you are on the root pointer and that's null, you have to say false. The thing is not here. Remember, contains returns a Boolean. In this case, we say, hey, look, if we run out of road, in this case, our base case, if you run out of road for add was the new thing goes here. In our case, if you run out of road, the number wasn't here, right? So you just return false. So in this case, the root pointer is not null, so therefore we look at this data and we say, hey, if it's equal, so our second base case, right? First base case is, did we run out of road? Second base case is, did we find it? The answer is no, we didn't find the 3. So what is now our first recursive case? It's less than this, so I need to go to the left. So we recursively call, and the next level, again we check, is it null? Nope. Is it the thing we're looking for? The answer is yes. Bingo, we found it, so we return true. Does that make sense? One base case, if we run out of road, return false. Second base case, if we found it, return true. And then we have recursive cases, which is if it's smaller, search to the left. If it's bigger, search to the right, but we need to pass those returns back, right? So there's going to be a chain of returns coming all the way back up through all the function returns so that it can return the overall result, whether it's true or false. So makes the algorithm a little bit more interesting here, is that you're doing this return all the way back up the chain. How about 2? We're looking for 2. We say, okay, start here. Is that null? Nope. It's smaller. Go to the left. Is that null? Nope. It's smaller. Go to the left. Now we've run out of road, right? We follow the left pointer here, and the left pointer is null. So therefore, we know the 2 goes there. But we're looking for contains. We're not making new things, right? So 2 should be there, but we ran out of road looking for it. Therefore, the 2, we return false. So if you follow the same algorithm, I think you'll be able to find that you can search for these things, and it is a fast, again, log n algorithm, which is pretty darn good, right? The search algorithm is pretty fast. It's like, log n algorithm is like guess a number between 1 and 100. Every time you guess a number, you're cutting off half. And so, you can find, even with a list of 1,000 numbers, it should only take you 10 guesses. So that's the kind of speed we're talking about here. So hopefully that makes sense. And here's the very top level algorithm: running out a road, finding it, or else the two recursive cases. So if we want to now get more specific in our pseudocode, how would we start writing it? Well, if we run out a road, right? So again, we're past the data that we're looking for and the start node. The recursive private version is going to have a start node so that it can keep looking down the tree in each subsequent recursive call. So if the node passed to us is null, return false. We ran out of road, it must not be here. Easy enough. Our second base case here, right? This is one base case. Here's the second one. If the data we're looking for is my data, the node that you're on right now, then return true, because obviously you found it. Those are the two base cases. How about the recursive cases? Well, otherwise, if neither of those two things is true, then if the data I'm looking for is less than my data, this start node data, then I need to search at the left. But don't forget, return that result. Return the result of that recursive call, because that recursive call is going to return true or false, and maybe it's going to call something else, and that's going to return true or false, which has to come back up here, which has to come back up here, which has to come all the way back and return to the overall public client-facing method's return value. Okay, and of course the last case is if it doesn't go to the left, it must go to the right. There you go. So that's straightforward. Now if we look at the code for that, it shouldn't be any surprise how that works. Here's contains, public front end, returns a Boolean. Now notice add didn't, right? Add didn't return anything because there really wasn't anything to return, right? There wasn't any point in saying, well, I couldn't add it because this is all dynamically allocated out of heap memory. There's no Boolean necessary to say, hey, I couldn't add this thing. Yeah, if your system's that problematic, then you have bigger problems that you're going to have way before you get to here. But this one returns a Boolean because the whole thing needs to say, yes, it contains it, or no, it doesn't. So public facing, again, it's going to call the recursive version with the root, the overload that's down here. And so pass through the data, tell me where to start. If I ran into null, right? If the node that I am pointing at right here, if this is null, return false. If my data matches the thing I'm looking for, return true. Otherwise, if neither of those base cases is true, I need to recurse. So if my data is smaller, recurse to the left. If my data is not smaller, must be bigger, recurse to the right. And again, very important that we return the result of this, because that recursive call is going to return a Boolean. We have got to pass that back to the calling function, right? The calling method each time. So we're passing these returns all the way back up the chain to where eventually this one can return, right, the call to contains here. Best way to do this is look at your debugger. You might have to put in some extra statements that sets this thing, like rather than just returning true or false, you might want to set a variable, set that variable to false, and then put the, put some something there that either dumps it out or has a breakpoint to look at it before you return. But definitely go in and do some debugging if you're having trouble figuring this out, or draw it out on paper and see how one thing returns the value, one method returns it to the calling one, and therefore passes it all the way back up the set of calls. So that one should make some sense, I hope. Okay, we're also going to look at load from file, but man, that's awfully easy. Right? All you have to do, if in this case we want to return a count of how many things we loaded, we just write a loop that says, hey, while there's more in the file, read it and call add with that data. Increment the count and return it. There's really nothing to this algorithm. Load from file is darn easy. Let's see where that is. There's the load from file, right? I'm using a scanner because the file is tokenized. Really the only thing is grab out data, throw it into add. That's it, right? and then count the items just because it's kind of nice to know whether anything happened. In this case, I'm catching the file not found exception and saying, hey, if something wasn't there, then obviously I didn't load anything. They can see that I loaded 0. That's returned, so they have a way to check and see whether something bad happened. So there you go. All right. And one more to look at is if we want to do an in-order display. Now, supplier code shouldn't typically display stuff, but you might want to write that just because you're trying to wrap your head around how all of this stuff works. So we could do that, but of course you can convert this to a function that would, instead of display, it would return a string, right? Which would feel a little more like the code we just looked at for contains. But now an in-order display, rather than being a log n algorithm, has to visit every node, right? We're going to have to visit every one. So obviously this is going to be a big O of n, right? A linear algorithm. So how do we do this? If we want to do an in-order display, remember if you watched some of the original videos talking about trees, you saw the little tricks of doing in-order traversal. But what we have to do is that we have to end up traversing the tree and always doing left first, right? So do my left, then do me, then do my right. So in this case, do my left comes down here. Do my left, there's no left, then do me, so there's the 3, then do my right. There's nothing here, so I've done this, that returns, that's the 3, comes back here, do me, then that's the 8, then do my right, comes down here, it says do my left, comes down here, says do my left, there's no left, do me, that's the 9, do my right, nothing there, returns here, do me, that's the 11, do my right, do my left, nothing here, do me, do my right. That's how you get an in-order display. You've got to walk through that whole thing. So what's the pseudocode got to look like? Well, if this node isn't empty, right? Because if the node is empty, just return. So another way to say that is only run this code if it's not empty, right? You're going to by default return if it doesn't take any of these paths. So if the node that I'm starting at, the start node, isn't empty, display my left child's data, display my data, display my right child's data. That's the definition of an in-order traversal, right? Left, me, and then right. So that makes a lot of sense. What about the pseudocode? Well, pretty straightforward. If this node is not empty, call the display method starting at my left child, then display my data. Again, if the node has a toString, that's easy. Otherwise, and then, not otherwise, and then you're going to do all 3 of these things. Go to my left, show my data, go to my right. So how about the code for this? Right, I have this display code now. I have it commented out because I've changed my, I've tried to be a little bit better about using supplier code and not doing display within this, but you get the idea. So again, public facing display method doesn't return anything, doesn't need to in any of these cases. There's no returns, right? We don't have an exchange X scenario here. And then we have a private one that you pass just a start node. If that start node is not null, call display going to the left, print out my thing, go to the right. That's it. So very straightforward. These methods start making sense to you, I hope, as you see several of these recursive methods being discussed. Hopefully they all start making sense to you. Recursion is just a part of the way that we manage trees. It's pretty hard to do it any other way. It's a little odd at first for your brain to work on, but it's a really good thing for you to try. I really encourage you to write some of these things yourself. This is not a time to just go grab code, right? This is not just grab the code from the textbook or copy it from the internet. Nope, this is stuff that you need to work out for yourself. So make up some problems for yourself where you have data, and integers are fine, right? It's a fine place to start. You can think of a whole bunch of algorithms that you could write, and you can make yourself practice these recursive methods, writing them from scratch, thinking through them, and implementing them and testing them. So That's where we're going to stop with trees for the moment. There are still more interesting algorithms to be discussed, but some of those are a little more complex, and we want to take a little breather here, and we'll continue them next time. Things like delete. If you want to delete a node, you have some more complex scenarios to think about depending on where it is. And also, remember that all of the things that we talked about here are counting on the fact that we have a height balanced tree. The only way that we can get things like what we were talking about here with contains, right? The only way that we can get contains to be as fast as we want it to be is if we have a height balanced tree. So what happens when this tree gets very unbalanced? Well, our algorithm starts slipping, right? Our complexity starts going down the toilet. So how do we do that? How do we fix that? Well, all interesting things to discuss, but we'll save them for another video, another day. So thanks so much for watching these. I hope you're learning a lot about trees and how to code them up using recursion. So thanks, and continue on with the next video in the series if you have interest.